To make a continuous time filter and use it as an equalizer, you need a zero pole response. Because of the zero, you get high frequency boost, and of course, at very high frequencies, it will always roll off. Okay, and we prefer it to be differential so that we can drive it differentially. So source follows output impedance. What about it? Yeah. So I would, okay, that's true. Actually, with the inductive boost, yesterday we said that with the second order system, you can get boost. So with that also, you can equalize the response. Okay, but that boost can be very sharp because of the second order. So let's say that for now, let's restrict ourselves to trying to make this type of response. Okay, where this is the gain of the amplifier versus frequency, and here is the zero, and here is the pole. So let's take a differential pair and tell me how you might be able to get a response like this. So you want to get the capacitive part, you want to connect a capacitance from the input to the output. Yeah, that is possible. So essentially, this is your amplifier, and this is loaded by resistors, and you want to connect capacitors across the transconductor. Yeah, this will give you some response like this, or you have to cross connect it. Actually, not the sign should be this way. Okay, so you do get a response like this. What is the potential problem with this? Yeah, related to that. So what happens to the stage that is driving it? Yeah, essentially it has to drive whatever current goes through the capacitor, it has to drive that. Okay, and that can be a problem because when it is boosting, most of the current is coming from the capacitance, not from the transconductance, right? So the current through the capacitance can be quite large, and that has to be driven from the previous stage. So let's say we don't want something like this. We want the input to look like the gate of an amplifier, the input of an amplifier, so that it presents a reasonably high impedance. We know that even the gate of an amplifier has capacitance, so it is not very high impedance, but something like that is much better than what we have here. How can we do that? Yeah, how can we make the gain of an amplifier have a zero? Feedback path, okay, that's a possibility. Essentially, that is what this is, but you don't want it this way. Let's consider feed-forward amplifiers. So, if you want a response that is rising with frequency, you have to use an inductor or a capacitor. You can't just have resistive circuits. That is very clear, right? So now, how do you make an amplifier whose gain is dependent on not the transconductor but some other component? I mean, you must have studied this, right? Huh? Put the capacitor in the source. What were you suggesting? Okay. Why will that make it independent of GM? No, that will convert a capacitor to an inductor. So that is not so much what I am interested in. I am only interested in making the gain of the amplifier dependent on frequency. So that means the capacitor has to play a role somewhere, and the simplest thing to do is to use degeneration, right? You use degeneration to make the gain of the amplifier independent of the active element, isn't it? So if you use degeneration resistors, Rs, and if Rs is much greater than the reciprocal of the GM of the transistor, the gain depends mostly on Rs, not on GM. Okay. Of course, this is frequency dependent. So what is the gain of this amplifier? If you have Rs and RL by Rs. Okay. But Rs can be replaced by something else. So he says you replace it with the capacitance. Okay, you can do that also. CS. What is the transfer function of this? RL into GS plus CS, SCS. So this gain changes to GS plus SCS. Is this correct? Somehow we have a continuous time response with only a 0 and no poles. No, even without the load capacitance. So this suggests that what does the Bode plot of this look like? It looks like whatever I have already drawn here. What is this point? This point, that's the 0 of the, this is GS by CS. So GM, why will GM drop? Of what? GM of the transistor is a constant, right? Let's say there are no parasitics. Okay, let's say there are no parasitics, so it is an idealized condition. So my question is, will the gain keep going up like this? There is no CCS here.
We have argued the case for CS with the GMR plus 1.
Yeah. So? Okay, where will the pole be? What is the maximum gain of this amplifier as you go to extremely high frequency? Yeah, what is the gain? GMRL, right? So it starts with being GS times RL and it goes up to GMRL. When these two capacitors are dead shorts, then this RS doesn't come into picture. Okay, so you have a regular differential pair, that's all. So the highest gain is GMRL. So what is the value of the pole? Again, this is a first order system, so the slope of this is 20 dB per decade. You know the value of this and you know the highest gain, so you should know the value of this. What is it? Huh? It's just direct proportionality, right? So GM by CS, approximately. The ratio of this frequency to this value should be the same as the ratio of this frequency to this value. Isn't it right? So by placing a capacitor in the source coupling of the source coupled pair or the differential pair, you can get a gain that is increasing with frequency. But of course, the gain will not go above the gain of the differential pair, the conventional differential pair. Okay. So essentially, you are reducing the gain at low frequencies and getting a, that's why you are getting a high frequency boost. Okay. And if you evaluate it properly, you will see that the gain is, as I said, GM by 1 plus GM times the impedance that is degenerating the source of the transistor, which is the parallel combination of CS and RS. Okay, and this itself is this is the transconductance of the block. So the gain of the amplifier is this times RL. So you can see the 0 is at 1 over CS RS, and the pole is not exactly at 1 GM by CS. It has this modifying factor. But if GM is much more than 1 over RS, you will get the pole to be approximately at GM by CS. So this is also a way to get high frequency boost. So over a certain range of frequencies, you will get high frequency boost. And in addition to this, because of all the other parasitics, the gain won't be like this. It may fall off at higher frequencies. And if you are talking about particularly high frequency circuits, these frequencies can be inside this range of boost, so that you don't get such a high boost. Maybe you will get something like this, but because of parasitic poles, it tends to fall off already. Okay. But there is a range of frequencies that you get a boost at. Now the difference between this type of boost and what you get with a second order system is that in this case, in case of the first order with a 0, you can practically get any boost you want. That is boost here I am talking about compared to the DC value. That is what is of concern. Of course, you can't have the gain to be very small, then you will end up transmitting a very small signal. But besides that, essentially boosting high frequencies or de-emphasizing low frequencies, they are the same thing as far as the equalized response is concerned. Okay. So with a 0, you will get a response that's like this, which can be over a wide range, at least for relatively low frequency circuits. Now with a second order system, if you define the magnitude of the boost, that is related to the quality factor of the circuit. So you have no freedom to set the shape of the boost. Okay. So you will get, here also you have no freedom, but it is more gentle. In case of a second order system, you will probably get something like this. Okay. It's very sharp. The boosted frequencies are not in a wide range. Okay. And that range also depends on the amount of boost that you get. So if you use a very high order system, you can get very large boost, but that will be a sharp peak, whereas you want boosting at over a wider range of frequencies. Okay. So this is for the first order system, it goes up at 20 dB per decade. But if you look at the attenuation of a transmission line, that's about 10 dB per decade. There are various causes for attenuation of a transmission line. There is series loss and shunt loss and so on. But because of series loss, the attenuation will be about 10 dB per decade. So you want a gentle boost, but over a wide frequency range. You don't want a very sharp boost. So something like this is does a better job than a second order filter generally. But still, you have very limited degrees of freedom. I mean, you can only choose like at what frequency you place the zero, so that it starts boosting up the frequencies. Whereas theoretically, if you have an FIR filter with a large number of taps, you can adjust the shape very finely. Right? You can get a response that is perhaps like this. Of course, that needs more taps, but you can get it easily. Second order system with a high Q. I mean, there are no zeros here. If you place a zero, then that may look something like this, depending on. I mean, in the second order system, I have only the transfer function looks like this. If this Q is very large, you will get a boost. Okay. So exactly the same response can be obtained by having maybe the series inductor or a parallel inductor. Series inductor also will do, right? So the response of a series RL has a zero, exactly like parallel RC. The impedance of a series RL is similar to the admittance of a parallel RC. Okay. The only problem with this is if you want to, let's see. So if you want to get place the zero at low frequencies, the value of the inductance becomes very large. Okay. So that's a practical problem, and on ICs you cannot get L values beyond, let's say, 10 nanohenries or something. So it becomes very hard to place the zero at low frequencies. Whereas with capacitors, you don't have that problem. You can adjust both the capacitor and the resistor to get a low frequency zero. Any questions on this? So you can also do it with parallel paths. You take this and you can add a capacitively degenerated differential pair in parallel, both driven by the same inputs. So this part gives you the DC response and this part gives you the overshoot when you apply a step. So the combination will give you the steady state plus the overshoot. Okay. When it goes through a low pass channel, the overshoot becomes flattened because of the low pass response, and you get something closer to a nice step that you want. How would you control the coefficient in this case? So there is only 1 degree of freedom, so the coefficient that I am talking about is, so let's say you have a boost here. If you lower the equalization coefficient, the response becomes something like this, or if you increase it, does this. So it gives you more or less high frequency boost. How can you get responses this way? What do you have to do to the circuit to get response? Either with this or the previous topology. Yeah, you have to either change the capacitance or the resistance in parallel with it or something. Effectively, they are the same thing. Okay, it's not very convenient as with the other case where you just switch the tail currents and the coefficients vary directly with the tail currents, but you can do that. Okay. Any questions on this continuous time implementation of the equalizer? So if you want a very simple equalizer, maybe something like this is more power efficient, because the power in this particular case, especially in the transmitter, depends on how much amplitude you have to drive. Okay. So in case of the FFE also, you see that if you didn't have any equalizer, you make an amplifier, you will drive certain amplitude. then when you add the equalizer, you will have to reduce that amplitude, okay, because the coefficients will, the post cursor and precursor coefficients will subtract from the main cursor. So the trade-offs would be, let's say you start off with an amplifier like this, and let's say this is driving a certain voltage to the channel. I mean, channel meaning there is a transmission line and terminated on the other side also with a resistance. Now, you find that this is not good enough, you need equalization, okay. This is an unequalized transmitter, and let's say this is driving 1 volt peak to peak, and you have to drive a certain amount of, I mean, it's not able to drive it properly, you need some equalization. So you can do two things. One is you connect, let's say you find that one tap FIR equalization is sufficient. So you connect one tap with opposite polarity and supply the delayed input, okay. That's what we do for the FIR equalizer. So let's say this size is, if this is 1, this is 0.2, okay. So what is the steady state amplitude of the output of the equalizer? Essentially, this is an equalizer with coefficients of 1 and minus 0.8. Sorry, minus 0.2. What will be the output value? If you apply a DC step, what will be the output value? The coefficients are this. If you apply a series of ones, what do you get at the output? 0.8. Yeah. So you get a reduced amplitude, but some equalization. Okay. And the extra power is 0.2. The power increased by 20%. Okay. So I'm just trying to show you the trade-off that is involved when you implement equalization. So let's say you want to do it the other way. You don't want this one. You don't want equalization. You want to use degeneration to get the same effect. Okay. So once you connect these resistors, what happens to the output amplitude? Will it reduce or increase? So let's say I use the same differential pair here and here, okay, and the same current. Okay, I mean the total current in these two is 1. Okay. So once you add this degeneration, the output amplitude will reduce, and then you can add some capacitance to get high frequency boost. So at a very crude level, they are more or less the same. Maybe this will consume lower power for a simple equalizer like this. But the advantage of the FIR equalizer is that you can make more complicated responses. So even if you get a lot of boost from this kind of circuit, you don't have control over the response. Meaning you will only get a response that is like this. You will not get a response that perhaps does this. Whereas with an FIR with sufficient number of taps, maybe you can get that. So for a simple equalizer, perhaps this would be preferred because you don't have to do anything, and perhaps it can also be realized with a little lower power. Okay. But if you want many taps of response, it's probably best to implement the digital equalization. It also has better control because you can digitally control the current and so. And the other thing is it will not suffer from the uncertainties of analog components. So analog components have a lot of tolerance, you know that. So and the GM also has quite a bit of variation. So this R and C will vary quite a bit. So that means that the location of the 0 can vary quite a lot. Whereas with this case, the location of the 0, or effectively the response is determined by the ratio of this current to this current, which is a very well defined quantity, okay, because of matching of components. Maybe the two transistors on different chips don't behave similarly, or if you make it today and if you fabricate another chip 3 months later, they'll have different characteristics. But if you generate all the currents from a current mirror, if this gives you 1, this always gives you 0.2. Okay, maybe in one case this gives you 1 milliamp, and in the other case it gives you 1.5 milliamp. But this will also correspondingly scale from 0.2 milliamps to 0.3 milliamps. So this also gives you a better defined response. So that is the reason to go to the digital implementation. Now, when you argue about power, etc., you have to also look at what else you need, right? For instance, to this I just feed the digital stream and that's it, I'm done, okay, to the continuous time equalizer. But this is not the complete equalizer. I need like 2 high-speed flip-flops also here to implement it, okay. So that also comes into picture. So on balance, the digital type of implementation may consume more power, but for more complicated responses, that's probably the only reliable way to implement the equalizer. Yeah, I mean, essentially in this case, you have to define the location of the 0, right? That is the coefficient, so to speak. That's the only degree of freedom you have. In this case also, the second coefficient is the only degree of freedom. I mean, you can increase both, but that's not the relevant thing. For equalization, the ratio of this to the main one is relevant. So similarly, in this case, the location of the 0 is the relevant quantity, and that you change by changing the value of R and C. Perhaps you can switch different values of R or different values of C if necessary. Here we don't need them. So that's the difference. So that's what I was saying. So in case of this equalizer, continuous time equalizer, all I need to do is I have the high speed, I have the bit stream, binary bit stream, and I feed it to these inputs. Whereas this circuit is not complete. I need two flip-flops between the two, okay? And I need a clock that is driving that. All of those consume power. So one crude way of doing it is in the frequency domain. So let's say your channel has a certain attenuation at fs by 2, okay? You want to place the 0 so that you get back this, you have a boost equal to this much at fs by 2, okay? So if the channel is a first order type of response, then it will compensate it exactly, right? But if it is not, then it will compensate it somewhat approximately. So you choose the equalizer by making the boost of the equalizer equal to the attenuation of the channel. Anything else? So in this particular case, it's quite simple, right? Meaning, so you know what this degeneration does to the gain of the amplifier. I am assuming you know this from prior experience, that this will make the gain more dependent on R, and also it will be different from the case when these two are shorted. Okay, it will reduce the gain, but reduce the sensitivity also to the transistor. That's the usual feedback argument. So in this case, at very low frequencies, clearly the capacitor doesn't come into picture, and at very high frequencies, this resistor doesn't come into picture, and the gain is that of the differential pair. Okay. So let's say the gain of the differential pair was this, that is when the sources are shorted, and when you degenerate it with the resistance, it falls down to this, and when you also degenerate it with the capacitance, it has to be this at low frequencies and this at high frequencies, isn't it? So when the capacitance is short, for those frequencies which where the capacitance is short, the gain is this. For those frequencies where the capacitance is open, the gain is this. So it has to go from here to here. Okay, is that okay or not convincing? No. Okay, firstly, in this case, the ground can be the line of symmetry, right? This is a differential circuit. Okay, so I mean, you don't see a path to ground, but this is a differential version of this circuit. Okay, and the 0 is a real 0. This is not a purely imaginary 0, right? The 0 of this circuit lies on this is the S plane, and the 0 lies here, not here. So there is no frequency of a sinusoid for which this impedance looks like a short circuit. Okay. So if you have zeros on the imaginary axis, for instance, if you look at the impedance of a series LC, it will have zeros on the imaginary axis. So in this case, for some sinusoid that you apply, this looks like a short, whereas this 0 is not on the imaginary axis, it's on the real axis. So nowhere does it look like a short, at least for no sinusoid. Okay. So it's for this complex frequency that you can say it's a short or something. But the easiest way to see it is like when the capacitance is open and when the capacitance is short, it has to make a transition between the two, and you also know that it's a first order thing, so that will be at the rate of 20 dB per decade. Anything else? Okay, let's switch tracks a little bit and deal with one of the practical problems. So far we have talked about flip-flops and transmitters and so on, and all of these circuits look like differential pairs driving resistors. Okay, even the flip-flop, it may have 2 or 3 differential pairs, but that's what it is, right? And if you think back to your first assignment, the way you designed the differential pair was you wanted to get a certain output swing, and in a logic family, you of course make that more than the input swing that you need for full switching. So in that particular case, you design the differential pair to switch at 150 millivolts, but then you design the output to give you plus or minus 300 millivolts. How do you make the swing 300 millivolts at the output? So IR. So you choose I and you choose R. But you also know that resistors on chip, they have a tolerance of maybe plus minus 25% at least. Okay. So if you have a fixed I, then the IR can go anywhere from, nominally it is 300 millivolts, so it can be from 225 millivolts to 375 millivolts. Okay. And when the swing is small, you can have a problem, meaning it may not be able to switch the next stage properly. So what do you do? So you want to measure this voltage. Okay. So every flip-flop, you, let's say you measure this differential voltage and you tune the current with feedback. So one thing is, of course, brute force, you make it so that for the lowest swing it will switch. But then that is really a suboptimal design, because in this case it goes from 225 to 375. So the lower side is a problem because the differential pair may not switch. The higher side is a problem because something may go into a triode region. So that part will not get addressed. And secondly, this is a kind of really brute force way of doing it. So you have to over design everything. So that is one way of designing, right? You over design everything so that it becomes robust. That is like in very simple cases you can do that. As the design gets more and more challenging, it gets harder and harder to do that. Okay. So when you make a very simple circuit, you don't really think about like power dissipation of this and the noise of this and so on. So you just design something, and usually that is severely over designed. But let's say in this case we don't want to do that. Okay. And also it addresses only this issue, it doesn't address the other issue. Okay. So if the variation is very large, you can have a huge swing. So that means that you will, the only way to design it in that case is you leave enough margins everywhere. Okay. So that's a waste. So that eventually means that the minimum supply voltage you need to operate this circuit will be some value, whereas by more optimal design you could have reduced it to a smaller value. So the other suggestion is to you actually measure the output and adjust the current. Okay. Is that okay? Can we do that? How would we go about doing it? Is the PMOS to do what? Yeah, but I mean, this is switching logic, right? I mean, this logic can be either low or high. So what do you want to do? You want to connect a PMOS differential pair or a single PMOS transistor? Huh? Oh, you mean you want to control the resistors? Okay. I think he was talking about a different thing. He said you measure the voltage and control the current source, right? So, but yeah, this is fine. So, okay, one suggestion is to use PMOS resistors. And what do you want to do with this? So essentially the idea is he wants to make a variable resistor and tune the resistance to some value. Okay. Rather tune the resistance so that it gives you the right swing. So how do we do that? Okay. So, okay, various ideas have been proposed. First is measure the output, adjust I. The second one is make a tunable resistor, let's say using PMOS, and adjust that. So, and how do we do this? So, one suggestion, so this is just like a very high level architectural type of suggestion, right? So, one level you are saying you measure the output common mode voltage and adjust the resistance, and of course at this high level you can also say adjust the current. Okay. But okay, I want now to go into more detail. I don't, yeah, this is fine. How do we implement it? Yeah. Okay. So, but what do you do? So, you are measuring the common mode in a different place, right? Is that what you want to do, or you want to sense the common mode of this flip flop? So, essentially you are exploiting matching. You are saying that all PMOS resistors on the chip will have the same value. So, he is saying instead of trying to muck around with the outputs here, you have a dummy where essentially, so let us say if this is I by 2 has to flow through this, okay. So, you force a current of I by 2 through this, and you know what I by 2 times R, what is the swing that you want is, okay. So, you have this value and you compare that to the reference value and then adjust it by feedback, okay. So, let us show the details of the implementation. So, this is the PMOS resistance that you want to control, and to do the feedback we have the op amp, and this control can go to every other PMOS resistor, okay. And let us say we want, this is I by 2 and this is R, and in our particular case this should be VDD minus 0.15 volts, that is the reference. What about the signs of this op amp, which is positive, which is negative? Yeah, it is plus minus, which is plus, which is minus. Why is that? So, there is an inversion through the transistor, or if you break the loop here, everyone knows how to do this, right? Okay, I do not have to go through this. So, there is an inversion here, you do not need an inversion through the op amp, okay. And this control voltage can be propagated to everything. So, and similarly, instead of feeding back to the PMOS transistor, PMOS resistor, you can feed back to the current source. So, let us say you have this at some fixed value, V bias, and this is the current source, and I can control this as well. This again is at VDD minus 0.15 volts. So, now the current will get adjusted to a value where this voltage is VDD minus 0.15 volts. So, basically you try to keep the swing constant, okay. You cannot control the I and R individually, but there is no need to control that perhaps. So, you try to keep the swing constant. Now, let us say there may be cases where I want to use a resistor, I do not want to use a PMOS transistor, and that could be because generally transistors can have more parasitics than resistors. I mean, that very much depends on how you implement the resistor, but one of the reasons is, so let us say this is the substrate of the chip, the transistor will look like this if it is a PMOS transistor. So, it will have the gate capacitances from gate to the other terminals, as well as these diffusion capacitances and so on. But then if you have resistance on a polysilicon layer which is separated from the substrate, it can potentially have a smaller capacitance because it is farther away and it is not in direct contact with the substrate like the transistor is, right. Now, this very much depends on the resistivity of the polysilicon. If the resistivity of the material is very low, then you need a lot of material to make the same value of resistance. In that case, the size of this is much more than the size of this, and that may offset the advantage of distance. But if you do have high resistivity resistor, high resistivity material, then you can make a compact resistor which has a small parasitic, okay. So, I may not want to use a PMOS transistor. What do I do in that case? So, I want to keep the swing constant. So, what can I do? So, I do not want to use a controllable resistor like a PMOS, I want to use a physical resistor, but I want to keep the swing constant. Yeah, actually the second scheme is not dependent on this being an adjustable resistor, right. So, instead of this, I can have a physical resistor, I mean physical meaning a passive resistor, not a transistor, and the swing will get adjusted in exactly the same way. So, you adjust the current so that it has some dependence on the resistance, okay. So, this is basically what is the current in this, what is the current flowing in this. So, let me make this more general, let me call this some Vref by R. So, you have a current that has an inverse dependence on R, That is, if the temperature changes and the R changes, the current will change. Also, if the temperature, if the process changes or the resistivity changes, then the current will change. Okay. So this is a very frequently used bias, type of bias current. I think you already know. Of course, you can bias with constant currents, or you can bias it. You can make circuits where the GM of the circuit is a constant. Are you familiar with that? So if you're not, we can deal with it sometime later. But it's also some kind of feedback circuit where the currents adjust themselves so that the GM will be some equal to the reciprocal of some resistance or some reference conductance. So in this particular case, the current is inversely proportional to the resistance. So if you pass this current through any other resistance of the same type, let's say this is N-type polysilicon, and you take any other N-type polysilicon resistor, not necessarily of the same value. Okay, usually it's the material properties that change, right? It's the rho that changes, and also the temperature is common to the whole chip. That's the assumption. So let's say the current is Vref by Rref, which is Vref by the sheet resistance times L naught by W naught. Everyone is familiar with the concept of sheet resistance? Okay. So the resistivity of a bar of material depends on the length, the thickness, the width, and the resistivity of the material. Okay. So what is it? Rho L by WT. Now in an integrated circuit, you have the process determines what the thickness is, and what you have freedom as a designer is to adjust the values of W and L. Okay. Essentially, designing an IC is a two-dimensional process from the point of view of the designer. You can only adjust things in this, on the plane of the IC. You can't go into the depth. You can't really do anything that way. Okay. So that is fixed by the process. So you don't worry about this thickness because it's fixed. So this rho by T times L by W is the resistance, and this is known as the sheet resistance. And this L by W, if you observe, is this is W, this is the length, and you count the number of squares, okay, along the length, and that is the that is L by W. Okay. So if L is 4 times W, you have 4 squares. Okay. So this is the sheet resistance is given in ohms per square. Okay. It's a convenient way to specify the resistance, and also it has nice symmetry with the resistivity of the MOSFET, resistance of the MOSFET, which also has an L by W dependence. Okay. Everything has an L by W type of dependence when it comes to resistance. So similarly, you also don't specify the in case of, let's say that we take the capacitance of the same type of thing. So you have epsilon A divided by the separation between the capacitors, and the separation between the plates is something that is fixed by the process for parallel plate capacitors. So epsilon by D is given as the capacitance per unit area and so on. So you don't have to worry about that particular detail. Okay. So if you have this is, I call this the reference resistance, and it has a certain L by W, okay, and let's say you take this current and pass it through some other resistance of the same type, L1 by W1, what do you get? So you simply get a scaled version of Vref. It is Vref times some ratio of dimensions. The ratio of dimensions can be fixed accurately, so this quantity will also be an accurate ratio of Vref, accurate ratio or multiple of Vref. Okay. So you can generate this what is known as 1 over R current. It's generally referred to as 1 over R current because it has an inverse dependence on R, and you can pass it through resistances of the same type. That will give you an accurate voltage across the resistance. Okay. If you have resistances of different types, that is which may have different which have no correlation with each other. Maybe you have an N-type poly resistance and a P-type poly resistance. Then of course you need to make 1 over R bias generator for each type. Okay. Because if in the reference generator you use N-type poly and then you pass it through a P-type poly resistance, there is no reason to, in fact the sheet resistances are different. Okay. There is no reason to assume the same temperature dependence either. So they will not track, but as long as you stick to the same type of resistances, you can propagate currents which are inversely proportional to that type of resistance and pass it through resistance to scale the voltage. So that's a very common way of what is that, propagating bias voltages on a chip. So this kind of bias you use in the flip flop, you can also use it in the transmit driver, because you have load resistances that are on chip. Let's say we assume that it's on chip. In that case, you need to produce reliable, accurate swings, you need to have the tail current to have this kind of dependence. Okay. Any questions?